Hello, my name is Rebecca Muller. During this section, we're going to look at how we can do some expansions of binomials. That is, how do we find the values of x plus y raised to the nth power, where n is a natural number. We're going to look at the patterns that we wind up with, and the process we're going to use is going to end up being called the binomial theorem. Let's first look at some expansions that we know how to do by hand. We know that x plus y to the 0 power is equal to 1. X plus y to the first is simply x plus y. X plus y squared, we know that we end up getting by multiplying x plus y times itself in order to give us x squared plus 2xy plus y squared. When we multiply x plus y times itself 3 times, we can end up taking the product that we got when we squared, x squared plus 2xy plus y squared, and multiplying it times x plus y again. Here, let's multiply both x plus y times x squared first. That will give us x cubed plus x squared y. Now, 2xy times both terms gives us 2x squared y plus 2xy squared. And finally, y squared times both gives us x y squared plus y cubed. Combining like terms, we note there's only one term with x cubed in it. We end up having 1x squared y and another 2x squared y that we can combine to give us 3x squared y. We have 2xy squared and another xy squared, which gives us 3xy squared. And finally, our y cubed. Now, let's notice that when we continue with this process, we're going to end up having some patterns appearing. Looking back at the problems that we've just worked, note that originally we got a value of 1. In the second one, we have 1x and 1y. In the expansion of the squaring, we start off with x to the second power, which is the power we are raising the binomial to. In the second term, it drops by 1 power to have the first power, and notice it appears not at all in the last term. Likewise, the y term does not appear in the first term, and yet is an increasing in powers in the next two. To look at whether the pattern we recognize actually continues, let's look at our last example. We start off with x cubed, it drops to x squared, then x, and finally disappears altogether, or that is, it is x to the 0 power. And the y's, we start off with y to the 0 power, and then to the first power, squared, and cubed. The pattern that we notice with our variables, x and y, actually is also going to have a pattern in the coefficients. And now let's look at a way to see that pattern. We're going to look at something called Pascal's Triangle first. This is what Pascal's Triangle looks like. You begin with a triangle of all ones. To get to the next row of this triangle, we're going to begin with a 1 and end with a 1. But notice that the value of 2 is arrived upon by combining the two terms that are directly above it. In our next row, we end up starting with a 1. We get the value of 3 by combining the 1 and the 2 from the row above it. We get the value of 3 in the same manner, and then we end with a 1. That pattern continues. Let's look at what the next row of Pascal's triangle would look like. We know to begin with a 1. Our next entry we'll get by summing the two entries directly above it. 5 plus 1 gives us 6. Adding 5 plus 10 gives us 15. 10 plus 10 is 20. 10 plus 5 is 15. 5 plus 1 is 6. And we end with a 1. Now, what does this have to do with binomial expansion? Well, this has a relationship to the coefficients that we saw earlier. You may recall that when we had x plus y to the 0 power, the value of that was 1. When we looked at x plus y to the first power, our coefficients are 1x and 1y. X plus y squared, recall, gave us x squared plus 2xy plus y squared. We have a coefficient of 1 in my first term, 2 in the second, and 1 in the third. That's the 1, 2, 1 that we see on this row. The same thing carries on further on. Let's look at the fourth row, or the fifth row here, but the one that has 4 in the second entry, and see if we can figure out what it's telling us. What we end up getting is x plus y to the fourth power's coefficients. Here's how we're going to use this. We start off with a coefficient of 1 for our first term, and as we saw earlier, we'll have the x raised to the greatest power we have here, x to the fourth. So that's our first term in the expansion. Plus, the next term will have a coefficient of 4. We'll drop the power of x by 1, and we'll start picking up our y values. Next, the coefficient will end up being the 6. We'll drop the power of x by 1, so that gives us x squared, and the power of y will start rising. Then we'll end up having 4x, y cubed, and finally, y to the fourth power. One other thing I want to point out about the pattern has to do with the fact that if you look at the combination of the powers on the x and the y terms, you'll always end up having that equivalent to the power that you were raising the binomial to. In other words, in my first term, I have a power of 4. In my second term, on my variables, I have 3 powers of x and 1 power of y, which sums to 4. In the next term, x squared, y squared, 2 plus 2 gives us 4, and so on. Now, Pascal's triangle is a neat way to find the binomial coefficients. However, you can see that if I was asking you in order to do something like x plus y to the 13th power, it would take us a little while to run through the triangle and get to the correct row in order to be able to use it. For that reason, we're going to look at a more efficient way in order to find the binomial coefficients. In order to do that, I need to give you a little bit of notation to start with. We're going to look at factorial notation. Here's the definition. For any positive integer n factorial, that's that exclamation point, is equal to n times n minus 1 times n minus 2, and so on, until we get to 3 times 2 times 1. In other words, you start with the number n, and you multiply down until you get to 1. The other part of the definition is that 0 factorial equals 1. Now, I'm going to do an example here to make sure that you understand how to use the notation. Let's look at 6 factorial and make sure we understand what the notation is telling us. This means to start with the number 6 and to multiply times each consecutive integer until we get down to the value of 1. So it's 6 times 5 times 4 times 3 times 2 times 1. When you multiply this out, the result is going to equal 720. Now, the reason we needed to learn factorial notation has to do with this theorem. The binomial coefficient is defined as follows. For non-negative integers n and r, with r less than or equal to n, the symbol, which looks like parentheses with 2 numbers on top of each other, it's read n choose r, is defined as n choose r equals n factorial divided by r factorial times the quantity n minus r factorial. Now, let's see how we can evaluate an expression using this particular type of terminology or notation. Let's look at 10 choose 8. This is going to be equivalent to 10 factorial divided by 8 factorial times 10 minus 8 factorial. Now, 10 factorial, recall, was equal to 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which would take us a while to write down. Instead, what I'm going to note is that I have 10 times 9 times, and when I get to 8, I'm going to stop and note that 8 factorial would give us the multiplication from 8 down to 1. The reason I stopped at 8 is that, let me point out that in the denominator, we also have 8 factorial. Therefore, in my next step, I'm going to be able to divide out these expressions. Then we have 2 factorial. The 8 factorial, as we said, divides out. It's a common factor, or I should say it's a list of common factors because it continues down 8 through 1. Then we're going to have 10 times 9 divided by 2, which is equal to 45. Let's see how our graphing calculator can help us do the exact same things. We're going to go to the TI-83 and look under, we're going to look at 6 factorial first. Let's put the 6 in, and we'd like to get that factorial key. This is going to be under Math, and we're going to go to the Probability menu, and notice that number 4 under that has the exclamation point. When we enter that, we see the result we've gotten earlier of 720. You may be wondering where that 10 choose 8 is going to be on your calculator. Well, I'm going to look back at the math key in order to point out something to you. Number 3 has NCR, and we can think of this as abbreviating for our purposes N choose R. Now, we have to first put the number in of 10 on our home screen. So I'm going to go back to my home screen, put in the value 10, go to Math, Probability, use number 3, and then put in the 8. And we can see that the calculator will also be able to evaluate the same thing that we just found out by hand, which is very nice. Now, let's look at some summarization of what we know so far about the expansion of x plus y to the nth power. Since we start with x to the nth power and we work our way down to where the x value doesn't appear at all, then there are n plus 1 terms in the expansion. The first term will be x to the nth power. The last term is y to the nth. The exponent on x decreases by 1, and the exponent on y increases by 1 in each succeeding term. The sum of the exponents on x and y in any term is n. And the coefficient of x to the rth power times y to the n minus rth power is n choose r. The binomial theorem can be given in a summation format as follows. For any positive integer n, x plus y to the nth power equals the sum of terms of the following format, where r goes from 0 to n. The format is n choose r, x to the n minus r power times y to the r power. Let's try to use this formula in the following example. We want to write out the binomial expansion for 3x minus 2y raised to the 6th power. We're going to begin with the binomial coefficient of 6n choose 0. Now, in this problem, the first term is not just x. We think of it as being 3x. And so we start off with 3x being raised to the 6th power. Then we add to that the next binomial coefficient, which will be 6 choose 1. This first term, 3x, ends up decreasing in power by 1 to the 5th power, and the other term, negative 2y, appears. Then we end up continuing with this 6 choose 2, 3x to the 4th, negative 2y squared, plus 6 choose 3, 3x cubed, times negative 2y cubed. I need that cube on the outside of the parentheses here, my mistake, plus 6 choose 4, 3x squared, negative 2y to the 4th, plus 6 choose 5, 3x to the 1st, negative 2y to the 5th, plus 6 choose 6. 3x is noticed to the 0 power, so we don't have to write it down. Negative 2y is to the 6th power. Now, we can use our calculators in order to help us evaluate each of these terms. Let me go ahead and write down the middle step as to what we're going to end up with here so that you can kind of double check this as you're going along. Now, we have that this equals 729 x to the 6th, and that 729 comes from 3 to the 6th power, plus the 6 choose 1 gives us 6, 243 is 3 to the 5th power, times minus 2, and then x to the 5th y plus 15, which is the binomial coefficient, times 81, which is the 3 to the 4th power, times 4, which is the negative 2 squared, then times x to the 4th y squared. Now we're going to add to that the next term. Binomial coefficient is 20. We have 27, which would be the 3 cubed, times negative 8, which is the negative 2 cubed, x cubed times y cubed, plus binomial coefficient is 15. We get 9, which is the 3 squared, 16, which is the negative 2 to the 4th power, x to the x squared, y to the 4th, plus binomial coefficient of 6 times 3 times negative 32, which is the negative 2 to the 5th power, x times y to the 5th, and our final term is 64, y to the 6th power. In its simplified version, multiplying out, we get 729 x to the 6th minus 2,916 x to the 5th times y plus 4,860 x to the 4th power y squared minus 4,320 x cubed y cubed plus 2,160 x squared y to the 4th minus 576 x y to the 5th plus our 64 y to the 5th here and y to the 6th in our last term. Now, the final thing we're going to look at is it always necessary to do the complete binomial expansion if all you really needed was a single term? The answer, luckily, is no. To find the nth term of the binomial expansion, we are going to use, where n is greater than or equal to r minus 1, the following formula. That's n choose n minus the quantity r minus 1 times x to that power y to the r minus 1 power. Let's find the 15th term of the following binomial expansion. We have a squared plus b quantity raised to the 22nd power. Here, the value of n is going to equal 22. The value of r is 15. And really, that's all we need in order to be able to evaluate this. So what we'll have is 22, choose 22 minus 15 minus 1, x to the 22nd minus 15 minus 1 power, y to the 15 minus 1 power. Let's evaluate that. We get 22, choose 8, x to the, x needs to be actually, well, let's go ahead and finish this, and I'll substitute in. X to the 8th power, y to the 14th. Now, in our problem, x was actually a squared. So we're going to have a squared to the 8th power, and then our b value takes the place of y, and we have b to the 14th. Now, we're going to go to a clean sheet of paper in order to write down the final result here. You could be using your calculators in order to evaluate 22 choose 8. We are going to go ahead and say that the answer to this, though, is 319,770 times a to the 16th power, b to the 14th. Now, we've reviewed a number of things having to do with binomial expansion. We have the binomial theorem, Pascal's triangle, and you need to try a few problems on your own to become familiar with these.